the end of life on Earth as we know it. How can a lump of coal and a shining diamond be composed of the same material? Yep, that's carbon. Carbon is an element of life. It is said to be as the foundation of all biological molecules. Carbon compounds are present everywhere, in the food that we eat, the clothes that we wear, and even in the lead of the pencil by which we write. Carbon is without doubt one of the most versatile elements known to man, as can be seen by the fact that it is the basis of life on this planet. But what is carbon? Carbon with an element symbol of C, atomic number 6, atomic mass of 12, it belongs to group 14 or 4 in the periodic table. Carbon is the building block of organic chemistry. Before we go deeper, let us recall some chemistry basics. Molecular formula emphasizes the type and number of atoms. We can see here the elements, proportions, and types present in the compound, while the structural formula focuses on the connectivity of these atoms. Here you can see the geometrical arrangement of the atoms and elements. For instance, on your left is the molecular formula for ethanol, while on the other side is the structural formula of ethanol. Both are CH3CH2OH. Organic compounds are classified also according to the structural formula. Aliphatic is an open chain structure. It can be branched or unbranched. Cyclic. Cyclic forms a ring where the first carbon is connected to the last carbon. Aromatic. It forms a loop of electrons or sextet of electrons. Benzene, for example, is aromatic in form. Now let's go to our main agenda. When we talk about carbons, we're also talking about hydrocarbons. Hydrocarbons are simplest organic molecules containing carbon and hydrogen. Hydrocarbon. Hydrocarbons occur naturally and form the basis of crude oil, natural gas, coal, and other important energy sources. We have the so-called pure hydrocarbons or saturated hydrocarbons. These are organic compounds containing only carbon and hydrogen, but here's the catch. They have single bonds only. Alkanes are fully saturated hydrocarbons because it is made up of single bonds. They're also nonpolar, so they are soluble in carbon tetrachloride and benzene, but not in water. Alkanes are naturally colorless, odorless, and tasteless. Let me give you an example. Methane is the simplest alkane with a molecular formula of CH4 and the main component of natural gas. As we all know, that carbon has 4 valence electrons, thus giving way for these 4 hydrogens to bond in it. Yes, I can see the confusion in your face. Let's have ethane with a molecular formula of C2H6. It is the next simplest alkane containing 2 carbons side by side, each one of them bonded to 3 hydrogen atoms. Alkanes are named by using a prefix which corresponds to the number of carbon atoms present. We use the prefixes meth for 1, eth for 2, prop for 3, but for 4, pent for 5, so on and so forth following the prefixes in your geometry class. So we have CH4, so 1 carbon, we use meth, and since it is an alkane, we call it methane. If we have this example with 3 carbons, it is called as, correct, propane. If 4 carbons, good, butane. As a general rule, the larger and more complex alkanes are, the more densely their molecules can pack together, which means that they tend to be liquid or solid instead of gaseous at room temperature. So alkanes with 5 to 18 chains of carbon atoms like octane and gasolines are liquids at room temperature. Those with more than 18 carbons atoms like paraffin or other waxes are solid. By the way, series of alkane is called paraffin series. To easily write the molecular formula of alkanes, we use the formula CnH2n plus 2. We also have a hydrocarbon called alkenes and alkynes. Both follow the rules in naming alkanes and have the same general properties. What makes them different is that alkenes have double bonds while alkynes have triple bonds. Also, both are unsaturated, unlike alkanes, due to insufficient number of hydrogens. For instance, if we have 2-carbon alkene, we call it ethene. There's no such thing as methane, since hydrogen can't have double bond in a single carbon. So if we have 3-carbon alkene, we call it propene. Here we have butene, pentene, hexene. As long as it has double bonds, we will name it as an alkene. Series of alkanes is also called as olefin series. We use the formula CnH2n when writing the molecular formula of alkenes. How about alkynes? Same as with alkene, alkynes don't have methane. Instead, it has 2 carbons with triple bond called ethyne. Three carbons alkyne is propyne, so on and so forth. Series of alkynes is called acetylene series. We use the formula CnH2n-2 when writing the molecular formula of alkynes. Now, let's go way deeper. Are you ready? Okay. We also have this so-called branched aliphatic alkanes. Yes, it is branched because it has substituents of halogens or alkyl group. An alkyl substituent is an alkane missing one hydrogen. Example, we have CH4 methane. If we remove one hydrogen in methane, it becomes CH3. It is called methyl since it is an alkyl. C2H6 is ethane. Remove one hydrogen, it is called ethyl. So every time we remove one hydrogen in alkane, it becomes an alkyl. So if I have propane, it becomes propene, butane, butyl, so on and so forth. The nomenclature of branched aliphatic alkanes follows numerous rules, but let me simplify it for you. First, look for longest continuous chain. This will tell you the total number of carbons and identify the prefix that you will use. Number the carbons in the chain starting from the end nearest to the first substituent. If there are substituents that are the same number of carbons in from either end, start the numbering from the end nearest to the next substituent. When more than one of a given substituent is present, use a multiplying prefix to indicate the number of substituents. Use di for 2, tri for 3, tetra for 4, etc. And use the number assigned to the carbon to indicate the position of each substituent. Remember to use commas to separate numbers from numbers and hyphens to separate numbers from letters. There are no spaces in the final name. Let's have an example. Name the alkane shown below. By the way, using a line bond is quite convenient and time-saving rather than writing the entire structural formula. First, choose the longest, most substituted carbon chain. The longest chain here consists of 8 carbons. so the parent name is octane. Next, we name the substituents. They each contain one carbon atom, so they are both methyl groups. The name now becomes methyl octane. Next, we use the multiplying prefix di to indicate that there are two methyl groups. The name is now dimethyl octane, since you can see there the two methyl groups are present in the long chain. Number the parent chain from the end closest to a substituent. If we begin numbering the chain from the right, the groups are numbered 2 and 5. If we begin numbering the chain from the left, the groups are numbered 4 and 7. Therefore, we number the chain from the right as shown on the screen. The name is now 2,5-dimethyl octane, since you can see that methyl is found in carbons 2 and 5. Let's try this hydrocarbon. Again, look for the longest chain. So we count here starting from the left. Carbons 1, 2, 3, 4, 5, and 6. Knowing the longest continuous chain, we can say that it is a hexane. You can see methylene carbons 2 and 4 and ethylene carbon 3. So by using all the information gathered, we can say that this is 3-ethyl 2,4-dimethyl hexane. Haloalkanes or alkyl halides are alkanes that have halogen substitutes. It is easy to name. Name the halogen first, then if it is branch aliphatic, it must be in alphabetical order. Example, CH3Cl. Its IUPAC name is chloromethane. It can also be named as methyl chloride, but then we will follow the IUPAC naming. How about this one? CHCl3. We can see 3 chlorines attached to 1 carbon. It is correct, trichloromethane, known as chloroform. Tri since there are 3 chlorines. How about this? Still check for the longest branch, so therefore it is a butane, because you can see 4 carbon as the continuous chain. Then we need the halogen first, so we have bromine in carbon 2 and methylene carbon 3. So therefore this is 2-bromo-3-methyl butane. Very good. Now let's try cycloalkanes. Cycloalkanes are cyclic hydrocarbons, meaning that the carbons of the molecule are arranged in the form of a ring. You see that pentagon? Yes, that is cyclopentane. How about this one? Correct. This is methyl cyclopentane because we can see the methyl there attached to our cyclopentane. Now when it has more than one substituent, you start counting to the carbon that has the nearest substituent. Let's have this. Analyze the picture. We can see the substituent bromine, chlorine, and methyl. Correct. This is 2-bromo, 1-chloro, 1-methyl cyclopentane. Alkanes and alkynes follow the same rules, but this time all double or triple bonds must be included. Start counting with the carbon nearest to the double bond or triple bond. So basically, you identify and number the longest chain, change the suffix, and add the substituents. Let's have this one. Analyze the picture. Start counting from the nearest double bond. We have 6 carbon chain with a double bond, so this is hexene. Where can we locate the double bond? In carbon 2. So therefore, this is 2-hexene. How about this one? You can count either ways. So we have your 4 carbons, carbons 1, 2, 3, and 4. Double bonds in carbons 1 and 3. So this is 1,3-butadiene or buta-1,3-diene because double bonds are found in carbons 1 and 3, correct. Try this. Triple bond in carbon 1 and methyl in carbon 4 with 6 carbon chain. This is basically 4-methyl-1-hexyl. Okay, let's proceed to aromatic hydrocarbons. The aromatic hydrocarbons are unsaturated hydrocarbons which have one or more planar 6-carbon rings called benzene rings, to which hydrogen atoms are attached with the general formula of CnHn. Many aromatic hydrocarbons contain a benzene ring, also referred to as an aromatic ring. So this is benzene. Remember that you get a methyl group CH3 by removing a hydrogen from methane CH4. And in case of benzene, you get a phenyl group C6H5 by removing a hydrogen from a benzene ring C6H6. Like a methyl or an ethyl group, a phenyl group is always attached to something else. Example. That is a benzene with chlorine substituent. So this is called as chlorobenzene or phenyl chloride. How about this one? That's correct. This is nitrobenzene. Now, learning hydrocarbons is a tough challenge. I cannot give you all the examples since this one video is not enough to cover everything. And let me tell you, you are not forced to memorize all the rules. God, you will be overwhelmed with a long list of rules. Just take the general basic rules of the nomenclature. Also, practice makes perfect. So practice, practice, and practice. Learning hydrocarbons can't be mastered overnight. I hope you've learned a lot in this lesson. See you next time in daily lessons. Thank you.